got our timer, Jacob? Yep. Okay. In this lesson, we're going to continue our study of Modern Arithmetic 4. We'll be studying our second lesson, so this is lesson 2 as far as class lessons are concerned. Our second lesson in Modern Arithmetic 4. Modern Arithmetic 4, this textbook we're using, it's not organized really helpfully into articles or divisions for classes. So we're just going to go through as many articles as we can in each class, make sure we take our time, get through everything carefully, and just work our way through the textbook. In our first lesson, we took some time for an introduction to mathematics, and we discussed just the first 5 articles here in this book. We looked at the definition of a definition. We talked about what quantity is. We talked about multitude and magnitude. We talked about science and the principles of a science, which are the primary truths. The first, the simplest, the most basic truths of a science. And the reason why that's important is because what it means to be wise is to know the principles of a science, because the principles are the cause of the whole science. The primary truths of a science are called the principles. And then we learn that art is the practical application of a principle or the principles of a science. So when we learn the principles of a science, art is the action or the process by which we apply the principles that we learn. Okay? And that's what we covered in that first lesson. Now, as we get to Article 6, we get into some general descriptions or definitions about mathematics, which we should go over. And anytime we look at definitions, we want to compare them to definitions that we see in other textbooks, other studies, and so on. And in Article number 6, we see a definition of mathematics. Article 6, mathematics is the science of quantity. And would you say that agrees with what we see in our other mathematics textbooks and studies? Do you think mathematics is the science of quantity is a good definition of mathematics? Yes or no? Yeah, it is. Mathematics is the science of quantity. We study quantity. Quantity is anything that can increase or decrease. Mathematics is the study of quantity. Article 7, we read, the elementary branches of mathematics are 4. Now this is where this is going to get interesting. Actually, they give only 3, not 4. Arithmetic, algebra, and geometry. So in modern mathematics, this is where things start to get the branches of modern mathematics are 3 in number. The branches of modern mathematics are arithmetic, algebra, and geometry. And that's right out of the textbook. The branches of mathematics, and remember, we just learned in Article 6 that mathematics is the science of quantity. So modern mathematics tells us that the science of quantity, this is actually very important. Modern mathematics tells us that the science of quantity, if you want to know quantity, you need to study arithmetic, algebra, and geometry. That's not what classical mathematics taught us. Classical mathematics does not tell us that the science of quantity consists of the knowledge of these 3 studies. Classical mathematics tells us that the science of quantity consists of the study of 4 different branches: arithmetic, music, geometry, and astronomy. So here we see a very clear difference between classical education and modern education. And it's not just that modern schools do one thing and classical schools did something different. We just have different methods. We just have different styles. No, that's not what the difference actually is. The difference is that modern mathematics tells us that to have knowledge of quantity, all that you need to study is arithmetic, algebra, and geometry. That's what modern mathematics tells us. It tells us that to understand quantity, all you need to know are arithmetic, algebra, and geometry. And yet in our classical arithmetic course, we've learned that there are 4 species of quantity: absolute multitude, relative multitude, magnitude at rest, and magnitude in motion. There are 4 species of quantity, and there are 4 necessary mathematical arts or sciences. So modern mathematics represents a different philosophy of quantity that disagrees with classical mathematics. It's not just different methods. It's not just different ways of doing things. There's a fundamental philosophical difference between modern mathematics and what they call the science of quantity, and classical mathematics and what the ancient philosophers and wise men called the science of quantity. Modern schools do not teach what the wise men called the science of quantity. This is an important difference. So when we study these 3 subjects, we're not saying that this is the science of quantity. We study classical mathematics in the quadrivium because we believe that that is the science of quantity. These are simply the modern subjects that we need for a high school and college education. And that's the difference between modern mathematics and classical mathematics. Classical mathematics is the real study of the science of quantity. Modern mathematics is not the real study of the science of quantity. Modern mathematics is simply a modern school requirement, a program of math studies that's required by modern schools. And this is why we have to get these studies done, and we want to learn them well. We want to master these studies, but we do not want to allow these studies to hog up our whole education and keep us from actually studying the 4 classical mathematical arts. The branches of mathematics are not arithmetic, algebra, and geometry, but they go and include music and astronomy. Okay? We could say maybe that Article 7 is stressing the elementary branches and saying, oh, we're just getting started. We're just getting started in this modern curriculum. But these other subjects, music and astronomy, they're never introduced as branches of mathematics in modern math courses. All right? Let's go back to our text. Article number 8, the definition of arithmetic. Arithmetic is the introductory branch of the science of numbers. Arithmetic is the introductory branch of the science of numbers. Arithmetic as a science of just read that carefully one more time. Arithmetic as a science is composed of definitions, principles, and processes of calculation. As a science, arithmetic is composed of definitions, principles, and processes of calculation. As an art, it teaches us how to apply numbers to theoretical and practical purposes. So let's get out of this discussion of classical mathematics. In article number 8 here, in article number 8, we have a division of the study of arithmetic. We learn that arithmetic is the introductory study of numbers. Okay, and then we're told that as a science, so we can look at arithmetic from two different perspectives. We can look at arithmetic as a science, or we can look at arithmetic as an art. And I want you to pay attention to the difference between science and art. You'll hear the phrase arts and sciences all the time. I want you to see what the difference between an art and a science actually is. As a science, arithmetic consists of definitions, principles, and I think that there's just one more, processes. Processes of calculation. So as a science, we're learning about numbers. We're learning definitions of numbers and quantities. We're learning principles of number and quantity. And we're learning processes of how calculations are carried out with numbers. That's the science of arithmetic. Definitions, principles, and processes. When we talk about the art of arithmetic, we talk about the application of the science to theoretical and practical purposes. And I'll explain what this means. When we talk about arithmetic as a science, we're seeking to actually learn the definitions, the principles, and processes. And we can study that in a book, and we can gather all of that knowledge into our heads, and we can know the science of arithmetic. Science, remember, is knowledge. Science is simply knowledge of something. Science is knowledge properly classified. We can know the science of arithmetic, but that's only part of the study of arithmetic. The science of arithmetic is only a part. When we learn the science of arithmetic, the purpose of learning the science of arithmetic is so that we can apply it and put it to work. We can use it. This is what art is, the application of principles. We just learned about that. So as an art, after we've learned the science, we want to use the science of arithmetic. We want to apply the science of arithmetic to theoretical and practical purposes. We want to actually use it. We study the science of arithmetic so that we can use it. We can apply it. That's what art is. The art of arithmetic and the science of arithmetic. Sort of like the soul and the body. The soul has understanding and free will and reason, but the soul doesn't have those things for its own sake. The body is the instrument. The body is the machine that allows the soul to actually do work, to actually do things. Okay? God didn't create us as angels. We're not just spirits. God created us as never-dying souls, never-dying creatures made in his image. We have understanding, free will, reason, knowledge in our souls, but our bodies are the machines that God has given us to actually carry out the knowledge, the understanding, the reason, and the will of the soul. It's science and art, knowledge and practice, or study and use, science and art. So when we're learning definitions, we're studying the science of arithmetic. When we're learning principles, different concepts, we're learning the science of arithmetic. When we're learning processes, how to do things, we're learning the science of arithmetic. And then we turn with all that knowledge, we turn and we apply it, we put it to work for the solution of theories and problems. That's the real goal of our study of arithmetic, to actually use it, to enjoy the benefit of the art of arithmetic, which is the application of the science. Okay? That's article number 8 there in our book. So we're seeking to know both the science and practice the art of arithmetic. Article number 9. A proposition, let's make sure we learn these definitions. Remember, this is the science of arithmetic. If you don't learn the science of arithmetic, you can't practice the art of arithmetic. Article number 9, what is a proposition? A proposition is a statement of a principle or of something proposed to be done. A proposition is a statement of a principle or of something to be done. A proposition. It's a sentence, but it's a sentence of a specific kind. Proposition is a statement of a principle or of something to be done. And we're going to see that division of propositions into two kinds is important. Notice how here, when we talked about the art of arithmetic, we talked about theory and practice, right? Theoretical and practical purposes. A proposition, what we see there in this definition of proposition is that there are two different things going on. A proposition is a statement of a principle or of something proposed to be done. What is a proposition? A proposition is a statement. What are the two kinds of propositions? One is a principle, a statement of a principle, or a statement of something proposed to be done. And we're going to see that that's a problem. So a proposition is a statement of a principle or a statement of a problem. And you'll see why this definition of the proposition is important as we get through the rest of this lesson. Proposition is a statement of a principle or a problem. A principle is some truth. A problem is something to be done. All right? So that's the first thing. There's a division of propositions between principles and problems. And as we look at article number 10, we see propositions are of two kinds, and here we see our book making another division. Propositions are of two kinds, and this is going to look familiar because we've studied this elsewhere. Propositions are of two kinds. Demonstrable. You remember this or no? Demonstrable propositions and indemonstrable. Demonstrable and indemonstrable. Two kinds of proposition. Demonstrable, able to be demonstrated. Demonstrable propositions are able to be demonstrated. Indemonstrable are not able to be demonstrated. Can be proven. Indemonstrable cannot. Cannot be proven. Now, when I say something can't be proven, there's a couple different ways I can mean that, and you have to make sure you understand what this means. If you say something that's false, if you say that I killed, some person, and I tell you that cannot be proven because I didn't do it. It's impossible for you to prove that I killed this person. That's one way that we can say something cannot be proven. It's impossible to prove. It's false. Right? You understand that? Something that's false cannot be proven. But there's another kind of thing that can't be proven. Some things can't be proven because they're self-evident. And self-evident truths are truths that they don't need any proof because they're obvious. So, a proposition can be demonstrable because it can be proven. And another proposition is indemonstrable, not because it's false and can't be proven because it makes no sense, but because it's self-evident, it's obvious, and there's no way to prove it. There's simply no way to prove it because it's obvious. And we're going to learn about these indemonstrable propositions in the next article. So let's get back to the book. Article 11, we read about an axiom. An axiom is a self-evident truth. An axiom is a truth that no one can deny. No one needs it to be proven. No one will question it. It's self-evident. Everyone can see that it's true. That's what an axiom is. The reason why axioms are important is because if you want to convince someone of something, if you want to say something that convinces people, you have to figure out, how can I start? How can I start my argument and have people be on board with me? How can I get people to agree with me? Let's say I'm talking to a mixed crowd of people. If I have a mixed crowd of people, I have Christians and atheists. I have people who deny that God exists, and I have Christians. Can I start by quoting the Bible? No, because atheists don't believe the Bible's true. A quote from the Bible is not going to convince someone who doesn't believe the Bible's true already. Right? So if I have a crowd of people, all different kinds of people, and I want to argue something that will be clear to everyone who is present, I have to use an axiom. Because an axiom is a truth that's self-evident or clear to everyone. All right, and I gave you an example of this the other day. An example of an axiom. So an axiom is a self-evident truth. And an example of an axiom, we learn a whole list of axioms in geometry, in classical geometry. An example of an axiom is that a whole is greater than any of its parts. A whole is greater than its part. And the reason why that's self-evident is because it's the definition of a whole and a part. A whole is greater than its part. That's self-evident. So if you were a Christian and you were an atheist and you were a Muslim and you were a Hindu, I could say a whole is greater than any of its parts, and everyone here would say, yes, that's obviously true. That's self-evident. You understand that? So that's an axiom. An axiom is a starting point in reasoning that everyone will accept because it's self-evident. And there aren't a million of these. It's very hard to find an axiom. But philosophy starts with axioms. An axiom, according to Article 11 there, is a self-evident truth. And the reason why they're important is because when we need to prove something, we need to find a place to start our argument. And we start our argument with an axiom. Article number 12, a theorem is a truth to be proved. A theorem is a truth to be proved. And when it says to be proved, that means it's demonstrable, because obviously if we have to prove it, it is able to be proven. A theorem is a truth to be proved, and a problem, Article 13, a problem is a question proposed for solution. And I drew this illustration for you the other day in another subject, and it's back here today. There are two kinds of, we can divide propositions in two ways here, and we can divide them two ways here. And what that produces for us is a square, where here we have principles and problems, and here we have demonstrable and indemonstrable. We looked at this the other day. We see that an axiom is a self-evident truth. So an axiom is an indemonstrable principle. That was Article 11 there. A theorem is a truth or principle to be proven. A theorem is a truth to be proven. So there we have theorem. It's a principle or truth that is to be proven. An axiom is a truth that cannot be proven. A problem is a question proposed for solution. A problem is a demonstrable I actually listed this as problem here. It was something to be done. Something to be done. A problem is demonstrable. And what that means is that not only do we need to solve a problem, we also need to prove that the solution is true. So a theorem is a truth that is not an axiom. Make sure you understand this. A theorem is a truth that's not self-evident. We have to prove it. A theorem is not self-evident. And so you shouldn't accept a theorem. If someone tells you a theorem, if you read a theorem in the book, you should not just memorize it. A theorem needs to be proven. You have to learn the proof for a theorem. The same is true with a problem. You don't just accept the solution of a problem. You have to actually seek the proof of the solution of the problem. Article 13 tells us that axioms, theorems, and problems are propositions. Axioms, theorems, and problems are three different kinds of propositions. There's one more kind that's not listed in this book. It's listed in geometry. The other kind of proposition is a postulate. We use them in geometry. So we learned about propositions in Article 9. Propositions are statements of principles or something proposed to be done. We learned that there are two kinds of propositions, demonstrable and indemonstrable. And then we learned the definitions of axiom, theorem, and problem. Are we at time-wise?
31 minutes.
Good. Okay. So Article 14, axioms, theorems, and problems are propositions. Article 15, a process of reasoning. So we keep talking about how we have to prove things. We have to prove this. We have to prove this. Article 15, the process of reasoning by which we prove the truth of a proposition is called demonstration. And this is why I've said to you before, demonstration is simply another name for proof. Demonstration is proof. A process of reasoning proving the truth of a proposition is called a demonstration. Proof. So if someone says prove it, you can say demonstrate it. Get that in your head. Demonstrate means to prove. Okay? Article 16, what is a solution? We all use the word, but what actually is a solution? A solution of a problem is an expressed statement showing how the result is obtained. And I talked about this the other day with you. A solution explains how the result is obtained. So if I give you a problem and you give me the answer, do you have the solution? No. Getting the answer is not the solution. Getting the answer is not the solution. A calculator can give me an answer, but a calculator cannot give me a solution. What modern math teachers, what modern math textbooks and schools often do wrong is they set up a course where students get grades for giving them answers to problems, but they never give them solutions. And that's why kids sit around asking, can we just use calculators? Why do we have to learn this? We can just do this on a calculator. If the math class is wrongly set up so that kids get grades for finding answers to questions, the kids are right. You can do that on a calculator, but that's not what arithmetic is supposed to be. A calculator can give you a right answer, but a calculator cannot provide a solution. Because a solution, Article 16, is a statement that shows how the result is obtained. You can only give a solution if you know how to solve the answers. And I've seen some of you solve questions, find answers, but you have no idea how to actually solve the problem. You couldn't teach someone else how to find the solution. Or if you think that you can, for another problem, your solution won't work. And that shows that you haven't really found the solution to the problem. A solution explains how the result is obtained. And in order to learn arithmetic, you have to be able to explain how the result is obtained. That's a solution. Article 17, the term operation. Operation is applied to illustrations of solutions. And notice it says, as used in this book. Operation as used in this book. That means in other places, the word operation might not have the same meaning. And when we study this book, we don't care what it means in other places. We want to know what it means in this book. An operation is applied to illustrations of solutions, to illustrate a solution. Article 18, a rule. What is a rule? A rule is a general direction for solving all problems of a certain kind. A rule is a general direction that explains to us how to solve problems of a certain kind. Notice the key word there is general. A general direction. That means a rule will apply to many different problems as long as they're the same kind. Article 19, a formula. A formula is the expression of a general rule in algebraic language. Look at Article 19. A formula is the expression of a general rule or principle in algebraic language. Now, if any of you has any interest in science, science communicates by means of formulas. Science uses formulas. If you've ever heard of Albert Einstein's, have you ever heard of E equals mc squared? That was a formula developed by Albert Einstein. E equals mc squared. Well, that's algebraic language. That's the language of science. That's the language of physics. So when someone asks, why do I need to study algebra? Algebra is to be understood as a way of communicating. Notice it says a formula is an expression of a rule in algebraic language. So the reason why we study algebra is so that we can understand algebraic language, because we have to understand algebraic language in order to read and understand formulas in modern sciences. So we have a rule, which is a direction for solving problems of a certain kind, and a formula is a certain way of writing a rule. A formula is using algebra to write a rule using symbols. So if you want to learn how to calculate the speed, we talked about this the other day. If you want to learn to calculate the speed of a car, and you take a physics class, and in the physics class you want to learn how to calculate the speed or the velocity of a car, we can say that the speed of a car, the velocity of a car, is equal to the distance divided by the time. That's a formula. It's a rule for how to solve a certain kind of problem. Okay? I could write that in a sentence and express it as a statement. I could write it out as a rule like this. To find the velocity, divide the distance traveled by the time traveled. There, that's my rule. To find the velocity, divide the distance traveled by the time traveled. That's a rule for how to find velocity. Which of these is easier to learn and remember? The rule or the formula?
Formula.
The formula, right? V equals D over T. It's very easy to remember. It's very easy to think about, very easy to use. And this is why scientists and mathematicians like to communicate using formulas. They're very easy to remember and use. All right? So that's a formula. The difference between a rule and a formula in mathematics. That's Article 19. Now, where are we at time-wise?
40 minutes.
40? Okay, we've got more time. So you should understand the difference between a rule and a formula, okay? A unit. Now we're getting really more into the science of arithmetic. That, from Articles 1 to 19, was really introductory. It's talking about information that we need, more like preliminary information that we need to understand in order to get started with the study of arithmetic. And in this course, we're studying higher arithmetic. Now in Article 20, we begin to really move into the study of arithmetic, the science of arithmetic. So Article 20 is a breaking point here, where we get into the definition of a unit. Now we're talking about the theory of number. We're talking about the science of arithmetic. So what is a unit? A unit is one thing. It's pretty simple. A unit is one thing. A unit is one thing, or one. And we're told one thing, that phrase, one thing, is a concrete unit because it also identifies the unit of measure. The number 1 by itself is an abstract unit because the idea of the number is abstracted or taken away from the physical thing. We don't refer to the unit, we simply refer to the value, the number itself. A unit is one thing or one. One thing where the object is identified is called a concrete unit. One without any reference to any kind of unit or substance is referred to as an abstract unit. That's Article 20. Article 21, number is the expression of a definite quantity. Number is the expression of definite quantity. A number can be abstract when the unit is not named and we just refer to the number, or it can be concrete. A concrete number is a number where the kind of unit is also named. And we talked about this in a previous lesson, right? The number 5 is an abstract number. 5 feet is a concrete number. 27 is an abstract number. $27 is a concrete number. If the unit is included, it's a concrete number. If there's no unit and we're just referring to the number itself, that's an abstract number. Okay, that's Article 21. We're going to continue with Article 22 and then stop. So this is going to be the last article we cover. Numbers are divided into 3 different kinds: integral, fractional, and mixed. So let's look at 3 different kinds of number, 3 divisions of number: integral, fractional, and mixed. There are 3 divisions of number. Integral, fractional, and mixed. I remember when I was a student in school and I learned the word integer. This word integer, you'll always see this when you're studying math. I remember that word, I didn't know what that word meant, and I don't think my teachers ever told me what that word meant. We just use the word integers all the time, and using words like that when you don't know what they mean, because sometimes teachers just assume that you understand things, and you don't. Latin helps us because in Latin, this word integer is just an adjective that means whole. Integer means whole. So an integer, what kind of number is an integral number? A whole number. 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all whole numbers. They're all integers. Okay? Integral numbers. Whole numbers. Fractional numbers. The word fraction means broken. Broken into parts. An integer is a whole number. An integral number is a whole number. A fractional number is a part of a number, a broken number. Fractio in Latin means a break. So integrals are whole numbers. Fractional numbers are parts of whole numbers. And a mixed number is a combination of integer and fraction. A mixed number contains an integer and a fraction. So if I have the number 7, is that an integral number, a fractional number, or a mixed number? What is that? Integral, fractional, or mixed?
Mixed. Fractional.
It's integral. It's a whole number. It's integral. If I have the number 3/4, that's a fractional number. And if I have the number 7 and 3/4, that's a mixed number. Whole number, fractional number, mixed number. That's what's taught there in article number 22. Numbers are divided into integral, fractional, and mixed. An integral number or integer is a whole number. A fractional number is an expression for one or more of the equal parts of a divided whole, and a mixed number is an integer and fraction united. 7 is an example of an integer. 3/4 is the example of a fraction. 7 and 3/4 would be the example of a mixed number. Okay, that brings us to Article 22, which is where we're going to stop the content for this lesson. So to review what we've covered in this second lesson. We looked at the definition of mathematics. We said that mathematics is the science of quantity. Mathematics is the science of quantity. We looked at what our textbook taught us are the 3 elementary branches of arithmetic, or mathematics, The 3 branches of mathematics were arithmetic, algebra, and geometry. We compared that to the 4 branches or divisions of mathematical studies in classical curriculum. We showed how they're different. We then looked through some logical terms, or what I said were preliminary information that we need to understand before we get into higher arithmetic. We looked at propositions, different kinds of propositions, and then we named the different kinds of propositions: axioms, theorems, and problems. 3 of the 4 kinds of propositions. We then looked at what a unit is, what a number is, and 3 different kinds of numbers: integrals, fractional numbers, and mixed numbers. So we're getting now into the science of arithmetic. We've done preliminary work, we've done introductory work, we've talked about mathematics and about arithmetic. We've talked about logical terms that we need to use to discuss arithmetic, and now we're actually getting into the real science of arithmetic, talking about units, numbers. In the next lesson, we're going to go through all of the signs and symbols used in the study of arithmetic, and then on into the real core of the book. So that's all for this second class lesson on Modern Arithmetic 4.